We're looking at families of quadratic polynomial functions. We're linking to what we've learned before and summarizing. Then we're looking at determining equations given certain information. So we've got a few different types of quadratics. And let's remember that the other one that we look at that we probably started with was y equals ax squared plus bx plus c, and you've learned before that that's polynomial form. Okay. Number one on our list, y equals ax squared. So these have their vertices at the origin. When I say these, it's a family of functions, which means an infinite number. So the family is infinitely big because a is a real number except for 0. So let's have a look at that. In our graphs here, we're looking at this family, and I've put on a slider. It's a parameter, and you've seen before the dilation, and of course you know that is the dilation factor, and you can have anything except for a equals 0, which I've got it set to, and look, it turns into a straight line because you'll have y equals 0, and that's basically the x-axis. Alright, so it's a constant function, so we don't consider that a quadratic, and we know that the dilation is negative, so that's actually a known. Okay, so once we get a number greater than 1, so that's y equals x squared there, we get a vertical stretch, so it becomes narrow and pointier. When we have a decimal value between 0 and 1, like 0.4, it gets broader, and the same thing happens in the reflection. So we've seen that before, so that's nothing new. The second on the list here, parabolas with the turning point at 2, 3. Alright, again, that's a familiar one because it's the HK form, and very quickly, if we move and we see this purple one here, and we can change h and k, and that'll translate it. So if it's x minus 2, its turning point there is 2 to the right of the origin, which brings it up to 2, and the plus 3, as you know, moves the turning point up 3 units. So again, that's nothing new. That's the turning point form. The next one here, we see that we have something that's not quite in polynomial form, and it's not in turning point form. It's got an a, which is a dilation factor, but it's got a factorized pair of parts, and that gives us information about when it's factorized in that sort of way of the a outside. We've got a form that helps us identify the x-intercepts. The x-intercepts occur when y equals 0. And if you look at this expression, how the x-intercepts occur when y equals 0, so that would be the Null Factor Law in action there. Because the only way, if you think about it, the only way you can get y equal to 0 here is by, you basically got 3 things. It's the Null Factor Law with 3 parts. You've got a times b times c. Alright, a times b times c. That is a ridiculous looking c, sorry about that. And it's really just the 3-part Null Factor Law. So a won't equal 0 because of what we've established all over the place here. B could equal 0, and c could equal 0. And so for b to equal 0, you've got x minus 2 equals 0, and x would equal 2, and so our intercept is 2. Likewise, with this one, x has to equal negative 5 for it to be 0, for in turn for y to be 0. Switching back over to some graphs of this now, so we can see that there. Okay, so we've got our turning point at 2, sorry, at zeros, I apologise, not turning point. It's not in the turning point form. Alright, this one here is basically in the form such that we can see the zeros. So -5 we said was one of them, and 2 the other. Okay, so it doesn't directly tell us information about the turning point. Of course, from our previous knowledge we know how to do that, but that's for another video. Next on the list is another example. So anything in this form, they will have parabolas with X-axis intercept, or just the X-intercept. One of them will definitely equal 2. This one here depends on what the value of h is. So graphically we can see next on our list here would be that, and what we can do is move h around. So sorry, if I said turning point a moment ago, I mean 0. So basically that changes one of the zeros you can see is fixed here, alright, at 2, because you can see that there. But the other one moves because h is moving. So it has an interesting effect on the parabola. It doesn't just change h, it has to change a few other things, but it does fix in the 2. So that's an interesting phenomena there. Next on the list we have things ax squared plus bx. So that parabolas will have 2 x-intercepts and 1 will be the origin. So let's have a look at that one. So we can adjust a and b. So it's got 2 x-intercepts, 1 will be the origin except when b equals 0. So that's provided b doesn't equal 0. So you see you've got 2 x-intercepts, always 2, apart from that one case when b equals 0. And we can adjust a as well. Okay, now when we've got things in polynomial form, whether it's like this here or that here, it is much harder to see the effects of the parameters a, b and c and h. So more about that in a minute. And by the way, if you're feeling overwhelmed, this is not about rote learning this bit. This is about some understanding of some key concepts, and if you understand the key concepts, it doesn't require very much rote learning at all, very little. So the main parameters that we've looked above are a, b and h. We've looked at c, but mainly a, b and h, and of course they relate to things like transformations that we've seen in the past, which are dilations and translations. So they relate to those. Especially a and h, and when it's in turning point we also have k. The polynomial form doesn't lend itself very well to looking at key features apart from the y-intercept. It'll tell us what the y-intercept is. That's about it. It's got its place, the polynomial form, but if we're looking for key features, it is not very helpful in that sort of way. So that's why the other forms that we looked above, like the turning point form in that x-intercept form, basically are handy in that regard. So if you look at, for example, if something is in polynomial form, so this is in a case where we've let a equal, so for ax squared plus bx plus c, if we fixed a to 1, so it's just a monic, and we fix c to 0, so you don't write c down, we just change b, we can see a pattern, but it's not easy to really determine what's going on. We can see as we go through here we're changing just the b and the bx, and you can see a movement up and to the right, so it's like a linear movement of sorts. It shifts it along, and you can see a mirror image between b values for the x to the power 1 term, b values that are the same magnitude but at the opposite sign. You can see that and that Alright, so you can see the color coding. Pause the video if you need a closer look. But these things are, we don't do this, what we're doing here, very much, because the polynomial form is tricky. Okay, so that's why we often use the other forms, and that's what the focus of this video is on. To clarify, just some quick examples here. Pause the video or replay them if I've skipped over too quickly for you. We've got a family of parabolas have the form this, y equals ax squared plus c. For the parabola in this family that passes through these 2 points, find the values of a and c. Okay, so let's graph that first. So we've got ax squared plus c, and I've got that further down here. Okay, you can see c, so there's no bx term. So is that polynomial form or is that turning point form? It's kind of a bit of both. So it's handy once the bx term is not there, and i.e. the b is equal to 0. It's easy to see what the plus c does, and it's easy to see what the a does. So a is the dilation and c is a vertical translation. So it's a bit of a mix of polynomial and turning point form. So it's about, see what I mean by about understanding things. So moving on, we've got, how do we do this? We're given 2 points and the form of the equation. Simultaneous equations is something hopefully you've looked at in year 10. That's solving two equations with two unknowns in this case. We're given some information from the two ordered pairs above. So we use that. So they get that equation by subbing in to the original equation. They get these little equations 1 and 2. So y is 7 from there. Sub it in the position of y. A, you can see, where did the x squared go? Well, x squared is 1 squared, which is 1, so that's 1a. So we can just write a. C, we don't know what that is yet. And we do the same with equation 2 using this point here. So simultaneous equations, you might remember one of the elementary row operations we can do is subtract an equation from another, or add equations together, in other words. And if you go subtract 1 from 2, so 2 take 1, you get 3 equals 3a. Pause the video if you need a closer look, and a equals 1. So you substitute that value in, which is another strategy. So we have elimination up here and substitution down here, and you get c is 6, and you can substitute that back in. So you might need to remember your simultaneous equations from previous years. So here is something you should take down as a bit of a summary. So there's three things. If it's in this form here, number 1, we've got this one is useful if you've got 2 x-intercepts and the coordinate of one other point. So two intercepts, 2 x-intercepts, and 1 point is needed, and that can give you the rule for a quadratic. Number 2, okay, you should be very familiar with that one by now. That will give you they'll give you the equation for a quadratic, provided you have 1 point and you are also given the turning point. This one here, again, a little bit more awkward than the others, the polynomial form. You need 3 points. So very quickly I'm going to show you those in action. So that was important summary there, so make sure you've copied that down there. Moving on, so this one here, you got your x-intercepts and a given point. So basically you're going to use this one from up here, number 1. Okay, we got 2 x-intercepts and one other point, and you can see that we are basically subbing in the knowns given from the question there. So basically, if from our previous work, if the x-intercept's -3, it's x minus -3, which is x plus 3, x minus 4 because it's positive 4, and we also know the point 1 comma 24. So we put that into an equation using the form for the x-intercepts in one point, which is again that one, and we can get our rule. You don't have to expand it, you can leave it in factorized form like that. It's still a quadratic, because once you do expand it, you'll get x squared there. Don't expand it unless it actually asks you to do that. It's unnecessary usually. Coordinates of the turning point are given, and we've got one other point, and so we use that form from above the turning point form, and we substitute the given point in for y and for x, and it's from there, and we solve that, and then we've got our equation. Again, you don't need to expand that. And a parabola passes through 3. This might be new to you. You've got 3 points, so the rule has to be based on the polynomial form. So this is tricky. You've got 3 equations here. They're easy equations once you sub those points in. Okay, again, you're subbing all 3 given points into the polynomial form. There's the points again. So we can see we get 3 equations, and what you do is substitute from equation 2 into equation 1 and 3. The 0 is very handy here because that knocks out that term and that term. You've only got the third term left, so we know that c is 5. Okay, so that's the y-intercept, as I said before. So basically you sub that in to equation 1 and 3, and you can get somewhere with that. Then we've got 2 equations. Now they've called them 1' and 3'. They're basically updated versions. They're derived from basically equation 1 and 3. So that's why they've given them that name. And we can solve them simultaneously. It's quite easy by adding them together. And then you can use equation 1. Once you know there, you can use one of the equations to work out the total rule. Now this relies heavily on simultaneous equations. Okay, so simultaneous equations, something that is a prerequisite from year 10. Okay, simultaneous equations, elimination and substitution. So in end summary now, to find a quadratic rule to fit given points, you've got to first choose the best form out of the 3. Okay. So you got your 3 forms there, and remember they're the turning point form, the polynomial form, and the intercepts version of the formula too. And you usually need at least one other point, if not more. Sorry, technical glitch. You usually need 1 point or more as well. To quickly summarize, if you're given something like this, the first one we did, you just need 1 point plus the form, and you can get A, and therefore you can determine the rule. Basically, if you're in this form, you need 2 points because you need to determine A and C. You can see that these 2 here are very close. One's just got a vertical translation. And that's the one I said before, that's like a combination of polynomial form and turning point form. The third one there, we've got 2 points are needed for that, because you've got to find A and B as per the example, and 3 points are needed for if you've got it in full